Okay, well, thanks very much again for having me. And okay, so there's two parts to the talk. Let me see if I can share my screen. Right, so we're doing quite a bit of work on applications of machine learning and deep learning, in particular, to all sorts of problems in the mobile networking domain. And today I'll probably spend time on two topics. One is how to do analytics, actually more specifically how to do traffic decomposition, which is also kind of the foundations for the NetAI spinout. And in the second part, I'll speak a little bit about how to use machine learning in kind of a principled way to tackle network security problems, in particular, how to do intrusion detection at the network edge. Let's start with the first part. Yeah, so this is no news now. We're seeing kind of increasingly more services relying on mobile infrastructure and applications that now have very diverse performance requirements, things such as autonomous cars, industrial automation, e-health, and so on. So all these kind of need intelligent resource management in order to be able to kind of support this diversity of performance requirements, ranging from low latency for all these kind of gaming, for instance, applications, or reliability for cars, or high throughput for, say, immersive video streaming applications. So what the 5G community has been working on to enable this is a sort of a new paradigm called network slicing, which basically involves partitioning the physical infrastructure into logical networks called slicing. It slices each of which will serve a specific application. And that's basically a schematic here. And this is kind of nice because basically the expectations is that with this new paradigm, operators will be able to save on the total cost of ownership in the range of 20 to 50%. So you're moving all the infrastructure in the cloud, running maybe on general purpose compute in software instead of on dedicated devices. And thereby you're reducing the cost a little bit, while at the same time supporting this diversity of requirements. Now, to be able to manage and monetize network slices effectively, it is paramount to have real-time knowledge of the nature and origin of the traffic that flows over these slices. So how do you normally do that at the moment? So all this sort of work on stream classification is relying on DPI, or deep packet inspection. And there's multiple ways to do that. So most of the time you do it in hardware. That's really nice because it's extremely fast, but it's expensive because this is sort of dedicated equipment relying on field programmable gate arrays. And every time you have a new type of traffic, you need to basically upgrade the equipment completely. So the operation doesn't really scale. And, of course, there are all the costs that come with basically ditching existing infrastructure and putting new one in place. So to kind of overcome this cost problem, the other alternative is to kind of deploy software-based DPI modules. Now, the challenge here is that you're lifting a packet from the wire, passing it up to the operating system stack, and that introduces some latency, and also it's prone to packet loss. And irrespective of the approach, we are seeing increasingly more traffic being encrypted. So both of them will be challenged by this new change in the landscape. So what we have been working on with my team is basically this new concept called mobile traffic decomposition. So we were saying, what if we look at time series of aggregated traffic streams at different levels in the network, and try to see whether we can basically use deep learning to decompose those aggregates into time series that correspond to the different services that make up those aggregates. So of course, depending on the application, you would like to do this at different network levels. So maybe you have applications that require low latency, you do it at the level of antenna, but that probably requires a lot of computation. But then there might be applications where you, for instance, run a cloud around deployment, and then you want to do decomposition at the level of a range of base stations. Yeah. So this is what you see in the middle. or you want to do this at the level of an entire urban region just for, let's say, planning and optimization, global optimization purposes. And then there are some interesting things going on in the networks which make them sort of special. And that's the fact that you have all sorts of spatial-temporal correlations that are specific to mobile traffic. And this is something that we will try to exploit in solving this problem. And this is basically kind of building on the line of research that my group has been working on for quite a number of years now. So I'll go into the details of how we do this, but in essence, just to kind of, heads up, this is kind of what we primarily do with Net AI. Technology is patent pending, but at the same time, we have a paper that appeared at Mobicom last year. So, some information is in the public domain, so you can go and have a look. So what are the key challenges of doing traffic decomposition? Yeah. So, you're not decomposing a single signal anymore into multiple time series. Actually, you're decomposing more, but even if it was a single signal, there might possibly be a couple of solutions that solve the problem. Yeah. So there is this ambiguity. And now if you want to sort of, exploit any spatial temporal correlations in order to resolve that ambiguity, the approach is really not exactly trivial. So you can't really do modeling. You cannot really come up with some really nice closed form solutions. So, the immediate thing is, well, can we attack the problem with machine learning? And then, of course, another question would be, okay, why don't we just use some existing techniques that people have been using in other domains? So for instance, there has been work on basically single time series decomposition, for instance, using factorial hidden Markov models. But then again, here we're looking at decomposing traffic across multiple locations and deliberately exploiting these spatial temporal correlations that you don't really see when you're looking at the single time series. But this is precisely the goal that we are pursuing with this piece of work. Yeah. So how do you do decomposition when you're making observations even across an entire deployment, let's say at the city scale? So the solution we came up with, we call Microscope. So this is basically a framework that uses deep learning. It's not just kind of the neural model. And there are some really nice properties to this. Yeah. So basically, what would you do first? You would have a deployment, as you see here on the left-hand side. And you collect measurements at different locations. But then the first thing is, okay, if you want to process those measurements with neural networks, let's say, especially convolutional type neural networks that expect the input to be in a matrix form, you need to do some pre-processing first, right? Because basically the first bit is basically, how can I do this mapping without losing any, spatial information? Yeah. So for this, we use something that we didn't come up with ourselves, but there is a nice algorithm that runs in polynomial time called the Hungarian algorithm. So the idea here is that basically how to kind of move those points on a grid without introducing a lot of distortion. Then we have aggregated traffic snapshots on those grids. So basically, think about this if you want, almost as if they were images. So in an image, you have pixels of different intensities. So now I think about the intensity of a pixel as being, say the volume of traffic at some location. Yeah. And then you look at this over time. So it's almost kind of like a video sequence. So this is sort of the output over, let's say, a time window, historic time window that you provide to a neural model. And there are a bunch of options that one would explore in terms of what to use for decomposition, depending on the level of accuracy, the level of complexity. So depending on the sort of performance, sort of complexity trade-offs that have to be achieved. And then there were a couple of interesting things we explored to basically accelerate the training process, including normalizing the output, what sort of loss function should be used for training. And as I will show later on in some of the results that we obtained, actually the choice of loss function makes quite a bit of a difference depending on which model you choose in the whole sort of decomposition sort of process. And then finally, what you will have at the output is basically having been provided with snapshots of aggregates over a time window, we will have basically snapshots of the individual services that make up those aggregates, which is what you see here on the right hand side. Yeah, so this can be not Netflix, Spotify, YouTube, or whatever else will be running in the network today, or maybe tomorrow it, might be traffic to do with, let's say, some autonomous vehicle type traffic. Okay, so let's just delve quickly through the different components here. Yeah, so the first point is, as I said, this pre-processing stage. Yeah, so you have basically antennas rarely being deployed on the grid. I mean, I think even in Manhattan, you don't see deployments on the grid anymore. So you will have to make this transformation from a point cloud to a grid without losing much spatial information. So what we do, basically, we overlay a grid with the same number of points. And what we're trying to do is a one-to-one association between each point in the cloud to each point on the grid while minimizing the spatial distortion. Okay, and there's a routine for this. I mean, I guess there are multiple ways to do this, but again, it's kind of nice. And then the next step is how to do the actual decomposition. So here we kind of came up with this brand new class of CNNs that are specifically aimed at decomposition, which we called three-dimensional deformable convolutional neural nets. And I'll show how they work, but kind of first just to give you a high level view. Yeah. So your input will be sort of 3D tensors that represent aggregate traffic snapshots across a deployment across a time window, which are then converted into some abstract maps that correspond to each different services. So here is basically that's done through these 3D convolutional blocks, and then we basically use a set of zipper blocks, and I can speak about these a bit more later if you want, but the idea here is basically you try to extract increasingly abstract features that will help in the final downstream task, which is, outputting information on a service by service basis. But if you're familiar with sort of, imaging applications, you'll see that this is sort of similar to what you see in the ResNet. Yeah, so you have different sort of staggered skips connections between the different blocks in the structure. And we used this previously for some different work when we were looking at traffic super resolution. So in that case, we were looking at, you had measurements collected in some points and you didn't have the full granularity, and we wanted to sort of blow up the sort of the image, if you want, of traffic consumption across an entire deployment without actually having to do very sort of fine granularity measurements. And then finally, we have a set of convolutional blocks that just sort of transform these features that have been extracted into snapshots that correspond to the individual mobile services that are of interest to us. So how does the 3D deformable CNN work? So if you're familiar with CNNs, which probably most of you are, you kind of you apply them on images. So you take like a rectangular kernel and you slide it across an image. If you do 3D convolution, you have the kernel being basically a cube, and then you scan the whole input with that cube. So when you do 3D deformable convolution, the first thing we do is basically learn some offsets that will be applied to that filter. And that's basically trying to understand to what extent there are correlations between different locations, both in terms of space and in terms of time that we see in, let's say, in a time window across a deployment. Yeah. So with that, so that's actually happening during the training. And then you have these offset maps, which are applied to the initial filter. So then, you spread that kind of convolutional filter across the entire input to some extent. And this is what you will use to scan and basically to learn the correlations between different locations in the input. So this is really allowing you not to be restricted to adjacent points in the input, but actually try to, look at points across an entire sort of window of snapshots. And then based on that, you have an output, which is this abstract map that we mentioned previously, and that later on will be used by the ZipNet, and the ZipNet will provide the actual traffic consumption on a service by service basis. Okay, so then what did we do to test this? So we implemented this in Python using TensorFlow and TensorLayer. And then we trained the 3D deformable CNN alongside other models using different loss functions and the Adam optimizer. For that, we use a high performance compute cluster with multiple GPUs. And we had a data set that was collected by Orange in a large city over approximately 90 days. There were approximately 30 services in that data set. We focused on, let's say, the heavy hitters, the 9 most demanding services, which you see here on the right-hand side. Yeah, so you see basically there's no surprise, kind of video and social media type of applications dominate traffic consumption. And then we performed evaluation at different network levels. So we did evaluation at the level of antenna, so RAN, radio access network, at the level of a mobile edge compute facility. So when you basically have, let's say, an edge data center that manages multiple base stations. And then we looked at also at core data centers. So when you have, larger geographical areas that are managed from a certain location. I mean, I guess I'll want to show you some of the stuff and not show you all the results with decomposition, but if there is interest, I'm happy to follow up offline. So probably the most important thing that you should care about is basically, okay, what's the best loss function and why is this 3D deformable CNN the best, which is of course the case, because otherwise I wouldn't be talking about this. But the idea is here that basically what we did to show that that's the case, we basically compared the output of different models with the ground truth and computed mean absolute error and normalized mean absolute error. And we looked at the performance with different loss functions, regression, mean squared error, and cross entropy. And you can see that basically performing decomposition with the 3D deformable CNN and cross entropy provides the best results. And another thing to observe here is that there are other models that actually provide better performance when trained with different functions. So for instance, for this task, the MLP, the multi-layer perceptron, provided lower MAE if it was trained with regression. I should just mention all the acronyms here for those of you who are less familiar with all these technologies. So CNN is convolutional neural net, so it's vanilla. LSTM is a long short-term memory, so it's a sort of a version of a recurrent neural network that just looks at temporal features. ConvLSTM, it's a mix of convolutional neural networks and LSTM. ZipNet is that block in the middle, which we previously used only for traffic super resolution. But then again, we just wanted to see, how performance would be if we just use that. And then we looked at a vanilla deformable CNN, which some people have been used for action recognition. And then we also looked at normalized MAE a bit more closely on a service by service basis. So I think that the takeaway message is here that normalized MAE is below 1.2%, which is actually quite nice in case you basically want to use these insights to drive the optimization of compute resources. Basically, if you want to decide how many virtual machines to spin up or how many containers to create, tear down, depending on the volume of traffic on a service by service basis. Okay, so maybe just a final example towards the end. So this is basically how decomposition will work in practice. Of course, I'm oversimplifying a little bit here, because if I was to show you 10 services, the slide would be a little bit too crowded. So imagine you have a traffic aggregate, which looks like the picture that you see here. This will basically decompose. Let's say these are kind of 3 services that make up that aggregate. Yeah. So what you see with red is the ground truth. So the neural net receives what you see on the top left corner, and then on the right, it's, well, the other plots are the sort of the decomposition output. And then with red, you have the ground truth, which is perfect ideal information that you normally don't have and you would like to have. And then with blue, you have the predictions. So you can see the predictions follow very closely the ground truth. Now, obviously, there are instances where, especially for Spotify, where you have like very bursty traffic, and this is kind of notoriously hard to predict. Yeah. So, but still, I mean, overall, the performance is pretty decent. Okay, I think I went quite at pace through that. So let's change gear a little bit and speak a little bit about classifying malicious traffic in the network, which is something that my cat is interested in as well, apparently. So why would you care about this? Yeah. So you probably read news all the time. So the cost of cybercrime is expected to exceed $10 trillion annually by 2025. Yeah. And this is due to a range of things. Malware itself might be causing damages worth of 11.1 billion only this year. The number of denial of attacks is increasing, has been increasing steadily over the past years. And then we're putting everything online now. So, I mean, I have countless devices in our home that are just going online, and this trend is set to continue. So we've been working jointly with ARM recently, and ARM have this scary estimates that in total worldwide, we will see something like 1 trillion devices being put online by 2035. So when you put everything online, it is, it's kind of, open up a can of worms, because a lot of the devices, don't really have proper security provisions. And you probably know of all sorts of like notorious instances, like, the Milai botnet that sort of took down parts of the internet just because, millions of IoT devices were recruited part of botnets. Sorry about that. Can you still see my screen? I had probably, no, let me try to check again. Can you see my screen?
No.
You lost me there. Okay, sorry about that.
It's okay.
Should be fine. Just give me a second. Well, let me just, here it is. What about now?
Okay, now.
Okay, cool.
We can see it now, yes.
All right, good. All right. So, okay, obviously, network intrusion detection now sort of starts to make sense, yeah? So what do I mean by that? So there are a few things here, yeah? So you're trying to monitor malicious activities that happen on the one hand when the attacker is outside the network. So somebody trying to compromise, let's say, an enterprise deployment. But at the same time, you might have actually attackers inside. So I mentioned these IoT devices. So you might have devices that have been recruited as part of a botnet, and they start kind of generating malicious traffic. Yeah. And this is something that we would like to detect. So now, of course, AI, machine learning type solutions are getting traction. And this is basically, the status quo, which is all these sort of signature and rule-based detection approaches don't keep up anymore. Yeah. So they have way too many false positives. They need to kind of, the rules have to be kind of kept up to date. Every time you have a new type of attack, you need to generate a new rule and so on. And it's very difficult for them to kind of detect unknown attacks. So sort of zero-day threats, if you want. So in conclusion, they're no longer sufficient. And of course, people are starting looking at deep learning-based approaches, at least as a second line of defense. And that's for a number of reasons. In theory, they should be able to kind of extract more sort of abstract features, and thereby understand whether there is malicious behavior that is hidden in large volumes of traffic. They may not need to look at every packet, so you don't really need to kind of do all this sort of, heavy lifting deep packet inspection. Maybe you do intrusion detection on a flow by flow level. And in theory, they should have better generalization abilities. And it's not entirely true, actually. And we're doing some work to sort of address this. So the problem with existing machine learning solutions is overall that they really learn superficially, meaning that they, unfortunately, mostly learn about the data that they were trained on instead of actually learning meaningful malicious behaviors. And that leads to a range of problems, but the most critical one, and I'll come back to this again probably until the end of the talk, is the fact that you can't really afford to have high false alarm rates in a practical deployment. Every time you have a false alarm rate, that means basically you need a network operator to kind of manually do a lot of inspection. So obviously that doesn't scale as the network speeds are kind of getting higher and higher. And then, you have more and more attacks appearing all the time. So, you train the machine learning model, but then you train it with examples. In those examples, you didn't have certain attack types. So every time you have a new types of attacks, if training was done based on the data, not based on the behavior, which is largely the case, you won't be able to detect this. And then there are very many types of traffic that on the surface look very similar, but in essence, they're fundamentally different. And you might want to apply different policies in terms of how to handle these types of traffic. And this might not necessarily be attacks, but might be things that you want to do in terms of traffic prioritization or scheduling or so on. And this is a challenge, how to basically improve this accuracy in distinguishing different types of traffic. And then ultimately there are a few trade-offs to be found here in terms of how much do you care about speed? You want to slow down traffic because you need to inspect it, or you care about accuracy. So what we've done with one of my students was to build this quite versatile framework, which we call ACID, which stands for Adaptive Clustering Based Intrusion Detection. And I say this is versatile because, again, like similar to what you've seen with Microscope, a lot of these building blocks, and I'll speak about them, can be interchanged with other features if, let's say a network operator so wishes to do so. And we wrote a paper about this as well, which appeared earlier in this year at Infocom. So the idea here is basically you take raw network packets, and the first thing you do feature extraction. So the first thing, what you see at the top is basically extracting statistical features based on header data. And then optionally, we can also look at payload features. So for that, we use some techniques that people have historically been using for all sorts of natural language processing tasks. So these basically don't really mean anything, given the payload is encrypted. It's really kind of building sort of abstract semantic representations of the payloads. And with these features, we build some flows, and then we provide these flows to a clustering network, which is kind of the core component. But then in general, if you want to use other clustering algorithms, you're welcome to do so. I'll show shortly why that's not necessarily advisable, but if there's been investment in some clustering approach that can be deployed. And then the downstream task is the actual classification. So you're extracting features, you did some clustering, and then you want to kind of classify the different types of traffic. Again, you can use any type of classifier that is appropriate here. In our case, we use a random forest just because that gives some degree of explainability, and it's simple, it's quite fast, and it's quite effective. So let's go through the different components. Actually, let's start by just kind of explaining what we had in mind. So our initial hypothesis was that actually, if you extend the set of features that characterizes flow with the cluster centers, you can only improve the classification results. And then we kind of came up with a theorem and we proved that that's the case. And I'll show at the very end, how much of a difference it makes to use these cluster-centered features with respect to any other features that are readily available. And this is really what sort of drives this whole adaptive clustering philosophy here. So what we basically do, and it's kind of it's a network. So basically, think about, if you look at the top, yeah. So you have kind of a sort of a parallel stream for every type of traffic about which you want to learn something, yeah. So you take the network flow features that you extracted previously, and the first thing is basically you pass them through encoders. The idea here is basically to reduce dimensionality. And then every kernel network will try to learn how far away an input that has been provided, basically within what cluster it will fit. So how far away, let's say, those features are from the distribution of the other features that are being learned. And with that, you'll obtain some similarity scores, but those scores you want to turn, convert into probabilities. So we use that with the softmax function, and then we basically, assign a flow label, like a class, to each of the inputs that are being processed. I think there was a bit more information here. Yeah, well, okay, I'm going to come back. So, I mean, just high level, yeah. So this is kind of nice because basically you don't have to have a lot of data for training. The architecture is rather flexible. So let's say you want to learn a new type of traffic, you go back and basically you just add a new encoder, a new kernel network, and that will learn the new type of traffic. So we haven't looked at basically doing sort of continual learning just yet, but basically by design, the architecture is, inherently suitable for extension and to support continual learning. There's probably some future role that we will be looking at. And as I will also show is that the whole structure is not very sensitive to small changes in the input. So to some extent, that's sort of the whole robustness and generalization abilities. And you will see that eventually will translate into very small false alarm rates, which is what I highlighted at the beginning. And in my opinion, that's one of the critical performance metrics of any intrusion detection system. So let's look a little bit at this. I mean, probably this is most of the maths that I will add. So I said, okay, you're going to use a softmax function because you want to translate the similarity scores into probabilities. Forget about the deal. This is kind of, bread and butter, how you kind of, transform similarity scores into probabilities. And then how do you train everything? So we train with mean squared error. So basically you want to see how far away an input is from a class. And then we trained the encoders with a contrastive loss function. So the idea here is that basically you want to bring together flows that have very similar features, while at the same time pushing further afar from each other flows that are of different classes, and the results will reveal, the effectiveness of this. And then for activation functions here, we use a sign-based activation function, which maybe is not intuitive. And then, I think I would be lying to say, oh yeah, we had this kind of in mind from the very start. So there was a little bit of exploration process, but our initial intuition was that, if we use something like this, it will allow us to kind of learn sort of more kind of sophisticated intertwined patterns in the input. Okay, so I already kind of said that, you can learn clusters on the fly. You have all this optimal separation through this adoption of the contrastive loss function. The fact that everything sort of happens on a say traffic type by traffic type basis also allows you to kind of better parallelize the whole architecture. So if you don't want to train everything on a same machine, you could even try to think about distributed training, so training on different types of machines. Okay, so, and then lastly, and the results will reveal, the whole architecture has a relatively small computational footprint, which is, very nice in case the interest is to deploy this at the edge, for instance, on a home router or on routers that, serve small enterprises. So let's look at some simple examples here. So we were basically interested in how the adaptive clustering network will work in terms of classifying all sorts of data sets with different complexity with respect to other clustering algorithms, right? Remember I said this is kind of modular. You could freely choose other clustering approaches. So here we looked at, complex nonlinear manifolds, basically the whole deal with concentric circles. Then we looked at inputs that had sort of intertwined class boundaries, the two moons example, blobs. So this is kind of, when you have Gaussian distributions that are typical to kind of linear classification problems. And then when the input sort of, has both nonlinear and intertwined class boundaries. So you could use k-means, you could use spectral clustering, you could use db scan. Problem is none of them will basically tackle clustering correctly of all the examples. Actually, k-means fails in all cases with these examples. And then spectral clustering has a hard time classifying, well, and db scan at least two of these, yeah. And instead, our adaptive clustering approach works quite nicely, irrespective of the type of data distribution that we're trying to classify. So I guess the most interesting part is this sort of sine cosine, where basically the whole sort of class boundaries are really hard to detect. So you see basically the output is extremely clean. There are no mistakes being made here, especially when you have crossing points. So let's look kind of zoom in a little bit and understand why that happens. So what you see on the left hand side is that concentric circle type data set. Have 5 classes, and then on the right you see this sort of the blobs data set. So the first step is to basically, you remember the encoder. So the first is basically to do dimensionality reduction. So now look at the points. You see the points are so neatly separated after the encoder. Yeah. So points of the same type belong to the same class are grouped nicely together, and then points of different classes are really nicely sort of pushed away from each other. So that is kind of the beauty of using this contrastive loss function. And then you say, okay, nice. This is kind of synthetic data. Show us the real deal with network security data. So we used actually 3 data sets for that that span approximately 20 years, 40 types of different attacks. We had raw network traces. You might argue with me later on that these are open data sets. Things might be different in practice. Yeah, I'm open to discussion, and maybe some of you in the audience actually have access to real data sets, and we can look at how to do some clever stuff with real data. So for the results I'm going to show, we have a kernel size of 10. We looked at both binary and multi-class classification. And we consider a couple of benchmarks. We use DAG-MM, which is kind of a recent model where it uses kind of a mix of Gaussian models and deep autoencoders. NBA-IoT, which uses deep autoencoders, deep neural networks, which are basically feed-forward neural nets, and then TRIDS, which is using this kind of similar to us, this natural language processing based and random forest approach. So the first thing we looked at was binary classification. So that means benign versus malicious traffic. And what I like you to see is that basically, we're doing much better than everyone else. If you look at accuracy, accuracy is way higher. And here, actually, if you look at AC hours, basically the first thing I'm highlighting is when you don't use payload features. So the simplest thing, which is basically just using statistical features. Yeah, false false alarm rate is almost 0, F1 score is almost 100%. When you add the payload features, which is also what TRIDS is doing, we increase accuracy to 100%, false alarm rate is 100, F1 score is 100. And again, I want to emphasize the difference here, although, you see accuracies being really high with other approaches, especially TRIDS, the false alarm rate of 1%, it's huge, yeah? So if you just think about a link of 1 megabit per second that is used, let's say 1 hour a day, that will basically, a 1% alarm rate will lead to kind of, 53,000 manual inspection, like alerts per day. So that means an operator will actually have to go and look at stuff 53,000 times a day. So it's obviously not acceptable in practice. Okay, so then of course we looked at multi-class classification as well. We looked at the a set of different types of traffic that we had in one of the data sets, and then of course I'm going to highlight the fact that there are some different numbers of samples here, different number of classes and so on, and then importantly the fact that irrespective of the class, what you see on the right hand side is that basically we never make any mistake, which is kind of nice. And then lastly, just to talk about complexity, I said, hey, look, this is nice, you can deploy at the edge. So we wanted to see how quickly this will run if you had like a sort of an emulated embedded environment. So we basically use the virtual machine with 4 CPU cores clocked at approximately 1 gigahertz, not a lot of power, 4 gigabytes of RAM, 50 gigabytes of storage. So admittedly, you can see something like this kind of in a home router, yeah. So we looked at inference times and model complexity in terms of floating point operations if the batch size is 1 and if you batch things. And clearly, if you batch things and you inspect larger batches, you can actually bring up some speed ups of 2 orders of magnitude, which is kind of nice. So that means you can deploy this at the edge. And we also looked at, okay, what happens if I use and I don't use payload features? And of course, if I use payload features, it takes a bit of time. If I don't, I can make an inference per sample in less than a millisecond. So that means basically, if I have delay sensitive applications, they will not suffer. It's rare that you have applications that have less than a millisecond latency constraint. I said, finally, I'll show you feature importance. So what you see on the right-hand side here are the different kernel features. And then, this is the whole picture shows like relative importance of the features. And then here you see the 15 most important ones. And I think the most important thing to remark is that those kernel features that we learned, the cluster centers, dominate the classification task. And, the difference in importance between the most important statistical feature and, well, actually it's a payload feature, and the least important kernel feature is quite substantial. It's probably twice as much. And then more about this whole idea is basically how does the model actually think about the data. So what you see here is this way of visualizing how decisions are being made by neural models. So for that, we use this T-distributed stochastic neighborhood embedding. So this is basically for data exploration. I want to see kind of high-dimensional data points into something that I can visualize, which is typically 2D or 3D. So what you see here is different types of traffic, how they are clustered. So this is kind of extracted before the final decision. So everything is kind of nicely grouped together for the different types of traffic. And then importantly, the different classes are well separated from one another. And this is basically what leads to this remarkable performance that we're able to achieve. Nice thing about this, code is open source. You can go and download it and play around. My student Alec actually has some nice work examples there. So it should be quite easy to get started if you're interested in this line of work. So let me kind of conclude quickly. If you use cluster centers to extract the input features, this kind of helps classifiers. you know, if you learn different classes with dedicated networks, you can reduce model complexity. I also talked about Microscope, how to basically do decomposition in order to kind of fuel this optimization of resources in future networks, including, well, 5G is not future anymore, including 5G. And I also showed that you actually, you can incorporate all sorts of neural models depending on the different management location and timescales that are of interest. But lastly, there's still a lot of work to be done in terms of improving traffic classification robustness, for instance. Yeah. So we didn't have time to speak about this today, but another piece of work we're focusing on with the team is what happens if you have adversaries that actually try to manipulate the input, try to introduce some adversarial features just to compromise the accuracy of classifiers. Yeah. So if you want, you've probably seen all these images where basically you add an additional pixel to an image of a panda and it will say this is a car, for instance. Yeah. So that's an example of adversarial input. So there's some work we're doing in that space as well.